Good afternoon everyone and welcome to my YouTube channel. So here today we are going to do every possible question that can come under A levels. So firstly, the question says that what are Boyle's law, Charles' law and Avogadro's law? What plots do you make to show a linear relationship for each law? So now, when we talk about Boyle's law simply states that the pressure of the fixed mass of dry gas is inversely proportional to the volume, provided that the temperature is kept constant. In other words, the pressure is inversely proportional to the volume, provided that the temperature is kept constant. This is Boyle's law. Now, when we talk about Charles' law states that the volume of the fixed mass of dry gas is directly proportional to the Kelvin temperature. So the relationship is a direct proportion. If the volume increases, if the temperature increases, the volume also increases. Now we also have Avogadro's law. Avogadro's law simply states that the number of moles is directly proportional to the volume. This means that then if the number of moles contained in a substance increases, even the volume will increase, because the mole is the amount of substance present in a certain thing. So now, if we are to draw the relationships, we are going to find that for Boyle's law, we are going to have a relationship that looks like this. So from the definition, we said that as long as the pressure is high, the volume will reduce, since they share an inverse relationship, meaning to say the Charles' law graph looks something like this. The other graph, this is the pressure against volume. If we say PV against the volume, for this is still Boyle's law, it looks like a straight line like that. If we say the log of P against the log of V, we are going to straighten our graph. It will look like something like this. So this is the graph of log P against log of V. If we look at the pressure against 1 over the volume, it begins from here, goes like that. So these are the graphs of Charles' law. Now they wanted the linear ones. So meaning to say we can take which ones are straight lines. We can take this one, or this one, not this one, because this is not linear, it's a parabola. So now let's look at the Charles' law. We are just going to draw one plot. Under Charles' law, since the temperature is directly proportional to the volume, it simply means to say we are going to have a straight line like that. If one factor increases, the other also increases. So this one will be a volume against temperature. So the temperature has to be in kelvins. So the volume against the temperature. So the temperature in kelvins. So as long as the temperature increases, the volume also increases. When we look at Avogadro's, we are going to have a situation of a graph that looks like this. So we are going to say it will be like that as well. Why like this? Simply because as long as the number of moles increases, we expect a rise in the volume. Let's look at question 2. Question 2 says, a high-performance road bicycle tire is inflated to a total pressure of 132 pounds per square inch. What is the pressure in millimeters of Hg? So under this one, we know that 1 atmosphere, this is the conversion factor, 1 atmosphere is equal to, let me use red. We have 760 millimeters of Hg. This same should be equal to 760 toricere, simplified like this. We also have, this should also be equal to 1.0 101.325 times 10 raised to the power 3, or rather let me use the kilo. So this is equal to the kilopascals. This same value should be equal to 14.7 pounds per square inch. So these are the conversion factors. So having done that, we can now convert this to a pressure in millimeters per mercury, millimeters of mercury. So if we have the value of 132 pounds per square inch, we can multiply using the chain link conversion. We are going to put here down, we are going to put a number. Since the pounds is there, we are also going to put the pounds. Now we know that the pounds is equal to 14.7 per square inch. Then on top we are going to put the equivalence of the millimeters of mercury in a pound. So this will be equal to 760 millimeters of Hg. So when we multiply 132 times 760 divided by 14.7, we are going to get 6,824.49 millimeters of Hg. So this is our pressure in millimeters of Hg. Looking at question 3, we are told a woman has an initial lung volume of 2.75, which is filled with air at an atmospheric pressure of 1.02 atmospheres. If she increases her lung volume to 3.25 liters without inhaling any additional air, what is the pressure in her lungs? So if you look at this, they have not mentioned any temperature change. So we are going to assume that the temperature did not change. If the temperature does not change, we are simply looking at Boyle's law. Now by Boyle's law, we know that Boyle's law states that since the pressure is inversely proportional to the volume, P1 V1 should be equal to P2 V2. So this is according to Boyle's law. Now we know that our pressure is 1.02 atmospheres. Then we are going to multiply by our initial volume, which was 2.75 liters. Then we are going to equate it to our pressure number 2, which we do not know. Pressure number 2 times the volume number 2, which will be our 3.25 liter. So we are going now to divide this. So divide by 3.25 liters, divide by 3.25 liters. So when we divide this, we are going to end up with the pressure number 2 should be equal to 2.805 divided by 3.25. This pressure number 2 will give us 0.8631 atmospheres. So this is typical because, as you have seen, according to the question, the initial pressure was 1.02 and volume was small, meaning to say if the volume increases, we expect a reduction in pressure, which makes sense if our answer is 0.8631 atmospheres. A gas in a cylinder with a movable piston has an initial volume of 88.2. If we heat the gas from 35 degrees Celsius to 155 degrees Celsius, what is the final volume? So they have not mentioned anything about the pressure. So now if the pressure did not change, this simply means to say we are looking at Charles' law. So by Charles' law, we know the formula for Charles' law is since the volume is directly proportional to the temperature, therefore V1 over T1 should be equal to our V2 over a T2. So our V1, our volume number 1, we are going to find that it is equal to 88 milliliter over our temperature number 1. Now, the temperature always has to be in kelvins. So how we are going to be doing these calculations in this video, we are just going to be doing the calculation all together. So if the temperature is in degrees Celsius, we are always just going to be adding a 273.15. So we are going to say open brackets. We are going to have 35, then degrees Celsius plus 273.15. This should be equal to our volume number 2. Our volume number 2 over the second temperature is 155 degrees Celsius. Then we are going to add plus a 273.15. So when we do our calculations, we are going to cross multiply. So we have 88.2 milliliters over, add 35 plus 273, 308.15, which should be equal to V2 over 155 by plus 270. This will give us a 428.15. Then we cross multiply. So we are going to have, this is the same as having our 308.15 V2 should be equal to 88.2 milliliters times 428.15. We divide by the 308.15. We divide by the 308.15. So when we divide this, we are going to get a 122.55 milliliters. Question 5. A male athlete in a kinesiology research study has a lung volume of 6.15 during a deep inhalation. At this volume, his lung contains 254 moles of air. During inhalation, his lung volume decreased to 2.55 liters. How many moles of the gas did the athlete exhale? Assume constant temperature and pressure. So immediately we are assuming constant temperature and pressure. We are looking at the Avogadro's law. So according to the Avogadro's law, our number of moles number 1 over the volume number 1 should be equal to number of moles number 2 over the volume number 2, since the number of moles is directly proportional to the volume. So our number of moles, our first number of moles, we have seen that it is equal to 0.254. So we have a 0.254 over our volume, which is a 6.15, just as we have seen. So now, if we have these, we can be able to equate our number of moles number 2, which we don't know. So over, we have our volume number 2, it decreased to 2.55 liter according to the question. So we are going to now cross multiply 0.254 times a 2.55. The liter, the moles should be equal to 6.15 N2. So dividing this 6.15, we are going to get our number of moles to be equal to 0.1053 moles. So these are the moles that the athlete remained with. Now the question is, how many moles of the gas did the athlete exhale? If we have this number of moles that the athlete remained with, to find the exhaled, we are just going to say exhaled should be equal to original moles minus the amount that he remained with, minus the remained. So we are going to have our original was a 0.254 moles minus 0.1053. So this one, if rounded to three significant figures, we are going to say the exhaled air. You will find that how much did he release? It is actually equal to 0.149 moles. If you are enjoying the video, just kindly like, subscribe, and share for more. So let's look at question 6. It says that calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 kelvins. Now, since we are provided with the moles, the pressure, and the temperature, we are going to use the ideal gas law. So according to the ideal gas law, we know that PV is equal to nRT. So our volume, making volume the subject of the formula, means divide pressure. So our volume is equal to, V should be equal to nRT over the pressure. So provided that the pressure is in atmospheres, we are always going to be using R of 0.08206. So this is the one that we are going to be using throughout in this video. So our volume should be equal to, our number of moles is equal to 0.85 moles, then times our R value, since our pressure is in atmospheres, will be equal to 0.08206 times the temperature, which is equal to 315 kelvins. Take note that the temperature also always has to be in kelvins, over, we are going to say, over the volume or the pressure, which is 1.37 atmospheres. So our volume should be equal to, if we multiply this, we are going to get 0.845, then times 0.08206, then times 315, we are going to get 21.84, then we divide by 1.37 atmospheres. So when we divide this, we are going to find that our volume will be equal to, divide by 1.37, we are going to find that our volume is equal to 15.94. The volume is in liters. Provided that you have the pressure in atmospheres, temperature in kelvins, your volume, the moles, your volume will always be in liters. Question 7. Calculate the density of nitrogen gas at 125 degrees Celsius and a pressure of 755 millimeters of mercury. Now, always, this is the quick way of finding the pressure in atmospheres. I told you that we are going to be using the pressure in atmospheres. So what we can do by the chain link conversion, it's 255 millimeters of Hg. We are going to multiply. Now, in 1 atmosphere, there are 760 millimeters of Hg. So this is our value. So we are going to divide this value in order for us to get the pressure in atmospheres. So we are going to get a value 0.9934. So now, in order for us to not even waste time, whatever pressure that you are going to have, as long as it is in atmospheres, as long as it's in this, we can always just be dividing by 760. So here we are just going to say 755 millimeters divided by 760 to get the pressure in atmospheres. So now, here they have introduced density. So we need to know how we are going to come up with the formula for density. So now we know to say our density is equal to not density. So we know from the ideal gas equation, the pressure, the PV should be equal to nRT. So we wish to come up with a density. So what are we going to do? We know that the number of moles is equal to the mass over the molar mass. So we can put this. So our pressure times volume should be equal to the mass where there are moles, mass over the molar mass, then times R times a T. So we are going to take this side. So we are going to have PV times the if we cross multiply, should be equal to the mass times the R, the T. So now what we are going to do is we are going to divide over the volume so that this volume goes. Here we can just divide over the volume. Since these are multiplying, it simply means to say it's still the same even if you did this. But since we want it to mostly affect the M, we are going to do it like that. So we are going to have P times should be equal to our mass, which is equal to mass over volume. We know that density is equal to mass over volume. So we are going to have a D where there is M over V, D times R times T. So now when we do this, we can be able to make D the subject of the formula by dividing RT. So our density is equal to pressure times the molar mass over the RT. So we know that the density now should be equal to our pressure. We found it to be 0.993. Then we have times the molar mass. So what is the molar mass of nitrogen gas? Now remember, nitrogen gas is diatomic, meaning to say it will exist like that as long as it's a gas. So the mass of hydrogen is 14. Then we are going to multiply by a 2. So we are going to have a 28. Then over, since we have used the pressure in atmospheres, we are going to get our R to be 0.08206 times what is our temperature. Our temperature, remember we were doing the conversion, it's in degrees. So I told you that we are just going to be adding a 273.15. So we are going to have a 125 degrees Celsius plus 273.15. So when we do this, we are going to end up with density to be equal to 27.82 over the when we multiply this, we are going to 0.08206 times 398.15. So when we divide this, now we are going to get 0.851 grams per liter. So take note of the units. We have the grams over the liter. So these are the units that we are going to be using for our density. Let's look at question 8. It says that arrange the following gases in order of increasing density at STP. So at STP, gases will occupy the same volume. Now, provided that they occupy the same volume, they just want us to identify which one has got the greatest density. Since the volume is the same, it simply means to say we know that the density is equal to mass over volume. If the volume is the same, the one that will have the greatest density is the one with the greatest mass. So we know to say neon as a gas, it's monatomic, meaning to say it will just exist like that. The mass of neon, we know from our periodic table, it's equal to 20.18 grams per mole. We are going to go to chlorine. Chlorine is the atomic. So the mass of chlorine on our periodic table, we know that this is equal to 35.45. Now since it's the atomic times 2, this will give us a 70.9. Let's look at our fluorine. Fluorine is equal to 19. So this 19 we are going to multiply. The molar mass of fluorine is 19, then we multiply by 2. So when we multiply 19 by 2, we are going to find our 38 grams per mole. If we go to oxygen, which is our O2, oxygen has got the molar mass of 16. Since it's the atomic, we are going to multiply by 2 to get a 32 grams per mole. So which one is the greatest? So if you look at chlorine, it has the greatest, meaning that this will have the greatest greatest density. So the order will be that neon will have the least density, followed by oxygen, followed by, we are going to have fluorine, followed by our chlorine gas. Let's look at question 9. So it's saying that a sample of gas has a mass of 0.311 gram. Its volume is 0.225 liters at a temperature of 55 degrees Celsius and a pressure of 8886 millimeters of Hg. Find its molar mass. So we know this is the ideal gas equation. And from the ideal gas equation, we have PV should be equal to nRT. So provided with that, we need to find a way of incorporating the molar mass. We know that the number of moles, so PV should be equal to our number of moles. Okay, let's just, yes, so our number of moles will be equal to, we have the mass over the molar mass, then we multiply times the R times the T. So the next stage that we are going to do is we are going to make the molar mass the subject of the formula. So we are going to have something like this. If we cross multiply, we are going to have PV times the molar mass should be equal to our mass times the RT. So then we divide by PV. So we are going to find that our molar mass will be equal to the mass times the RT over the PV. So this means that our molar mass should be equal to, what is our mass? Our mass is provided to be a 0.311 from the question, 0.311 grams, then times, we are going to have a for R it's 0.08206, then we have times the temperature. Now the temperature is in degrees. What I said, the temperature we are given according to the question, it's 55 degrees Celsius. So we are going to say this will be times a 55 degrees Celsius, then plus a 273.15 kelvins. So we are going to end up with, not kelvins, we are going to end up with a unit of kelvins when we add those. So over, what is our pressure? Our pressure, remember what I told you, if we have any pressure in atmospheres, in millimeters of Hg, to convert it to atmospheres, we are just going to divide by 760. So we are going to put our 888 divide by 760 not ATM. We have the millimeters of Hg over the millimeters of Hg, then times 1 atm. So in other words, we just divide those. Then we are going to multiply by our volume. So our volume, according to this, our volume is 0.225. So we are going to put it there. So we have a 0.225 liters. So our molar mass should be equal to, so when we multiply 0.311 times 0.08202 times 55 degrees plus 273, we are going to get 8.33746. Then we divide this by the outcome. So if I divide 886 divided by 760 times 0.225, I get 0.2623. So I'm going to get my molar mass to be equal to 31.93 grams per mole. Question 10. A 1 liter mixture of helium, neon, and argon has a total pressure of 662 millimeters of mercury at 298 kelvins. If the partial pressure of helium is 371 millimeters of mercury and the partial pressure of neon is 112 millimeters of mercury, what mass of argon is present in the mixture? So we have been told that the total pressure. So according to Dalton's law of partial pressures, the sum of the partial pressures is equal to the total pressure. So now the total pressure, I'll say P total is equal to 662. So in order for me to find the pressure of argon, I'll be able to form an equation to say the pressure of argon plus the pressure of helium plus the pressure of neon should be equal to the total pressure. So the pressure of argon is unknown. So we are going to say the pressure of argon plus the pressure of helium is equal to 341. So we have the 341 millimeters of Hg. Then we are going to add the pressure of neon, which is 112 millimeters of Hg. Then this should be equal to the total pressure, which is 662. So now 662 millimeters of Hg. So now when we add these two, 341 plus 112, Pa plus 453, which should be equal to 662. So when we subtract, we are going to get pressure number 1. Pressure of argon should be equal to 662 minus 453. So when we subtract these, which are both in millimeters of Hg, when we subtract these, we are going to get a value of 209 millimeters of Hg. Now that we have found our partial pressure of argon, we need to find now the mass of argon. So what we are going to simply do is let's just find the number of moles first. So we know that the PV, according to the general gas equation, PV should be equal to our nRT. So now our pressure is equal to, we want our number of moles, so we are going to divide over RT over RT. So our number of moles should be equal to PV over RT. So our number of moles is equal to, what is our pressure? So according to this, our pressure, which is our partial pressure of argon, was 209 millimeters of Hg. So as long as it's in millimeters of Hg, we are going to divide by 760 millimeters of Hg. Then we are going to multiply by 1 atm according to the chain link convention. So this is the pressure part, then times what is the volume. So according to Avogadro's law on partial pressure, the volume is taken as if the gas was alone in the container. So this 1 liter, we are going to assume that the gas will occupy the whole 1 liter. So 1 liter then over our R value, our universal gas constant, is equal to 0.08206 times our temperature. Our temperature is equal to, our temperature according to this was equal to 298 kelvins. So we are going to put it there. So we have 298 kelvins. So when we multiply, we are going to have the number of moles is equal to 209 divided by 760, 0.275. Then we are going to divide this by our 0.08206 times 298 will give us a 24.45388. So when we divide this, our number of moles will be equal to, we are going to get a 0.01125 moles. So these are moles. Now to find the molar mass, we know that the number of moles is equal to the mass over the molar mass, which means that our molar mass, when we make molar mass the subject of the formula, so we have the number of moles times the molar mass should be equal to the mass. We divide by the number of moles, we divide by the number of moles. So we are going to have our molar mass should be equal to, what is our mass? Oh, sorry for that. We want the mass, not the molar mass. We want the mass and not the molar mass. So our number of moles here, when we cross multiply, we have the number of moles times the molar mass, which should be equal to the mass. So this is the same as the mass should be equal to the number of moles times the molar mass. So what is our number of moles? So our number of moles is found to be 0.01125 times the molar mass of argon. Now our molar mass of argon is 39.95. So when we multiply these two, we are going to find that we are going to end up with the mass to be equal to 0.0125 times 39.95. This will give us a 0.449 grams. Let's look at question 11. Question 11 says that a 12.5 liter scuba diver tank contains a helium-oxygen-heliox mixture made up of 24.2 grams of helium and 4.32 grams of oxygen at 298. Calculate the mole fraction and partial pressure of each component in the mixture and the total pressure of the mixture. So now, provided with such a problem, the first thing that we are going to do is let's find the number of moles. So the number of moles of helium, we know that the number of moles will be equal to the mass over the molar mass. So the number of moles of helium should be equal to what is our mass. According to this, our mass of helium is 24.2 grams over the molar mass. What is our molar mass for helium? We are going to find that our molar mass is equal to 4. So we have over 4 grams per mole. Then when we divide this we are going to get a value of a 6.05 moles. So we have found the number of moles of helium. The other part that we need to do is the number of moles of which other substance is this? We have the number of moles of oxygen. Oxygen, the mass we have been provided, it is equal to 4.32 grams. So oxygen is the atomic, therefore it will be 16, which is on the periodic table, times 2 grams per mole, since there will be 2 of these. Then when we do 4 points that divide by 32, we are going to get a 0.135 moles. Then when we do this, we are going to find the sum. So the total moles, since these are in one container, so the total moles will be equal to the sum of the two. So the number of moles of helium times the number of moles of oxygen. So the number of moles of helium is 6.05 moles. Then we have times 0.135 moles. Then when we multiply this, when we add, when we add these, we are going to get a value of 185 moles. So this is the total moles. So now to find the mole fraction, therefore we can say a fraction is more like the mole of that substance over the total. So we can say that the mole fraction of, let's say, helium should be equal to the number of moles of helium over the number or the total number of moles. So the number of moles of helium, we know that that is equal to 6.05 moles. Then we divide this one over the total moles, which is 6.185 moles. So when we divide the mole fraction, we are going to end up with 6.05 divided by 6.18. We are going to end up with 0.9782. Now when we find the mole fraction of the other one, the mole fraction of oxygen, which will be the same, the number of moles of oxygen over the total, since we want a fraction of the whole. So the number of moles of oxygen, which is equal to, we have, let me move the screen a bit. We have, when we divide these, we are going to get a 0. We know that the number of moles of oxygen was found to be 0.135 moles. Then we divide this, divided by the total, which is our 6.185 moles. So when we divide these, we are going to get a value of 0.022. So these are the mole fractions. So the other part of the question says that calculate the mole fraction and the partial pressure of each component in a mixture and the total pressure of the mixture. So we also need to find the partial pressure. So now the partial pressure is found by, so we can say PV should be equal to nRT. So this has to do with the ideal gas equation. So let's say we are finding the pressure of first helium, which should be equal to nRT. When we divide V, we divide V over V. So the pressure of helium will be equal to, what is our number of moles? Our number of moles of helium was found to be 6.05 moles. Then we have times our gas constant 0.08206 times what is our temperature. So our temperature is equal to, according to the question, we were provided with 298 kelvins. Then we divide this by the volume. So the volume, according to Dalton's law, the volume is as if the gas were alone. We are going to assume that the gas occupies the whole volume. So we are going to have over a 12.5 liters. So when we divide those, we are going to get our partial pressure of helium. So 6 times that divided by 12.5, we are going to get 11.84 atmospheres. Looking at the partial pressure of oxygen, we are going to use the same approach. Should be equal to nRT over the volume. So our pressure, our number of moles of oxygen was found to be 0.135 moles, then times our gas constant 0.08206, then times our temperature, which is at 298 kelvins. We are going to divide this by the same. We are going to assume as if this time the oxygen occupies the whole volume according to Dalton's law of partial pressure. So the pressure of oxygen, the partial pressure of oxygen is equal to 0.2641 atmospheres. Let's look at our question number 12. So according to question number 12, in order to determine the rate of photosynthesis, the oxygen gas emitted by the aquatic plant is collected over water at a temperature of 293 kelvins and a total pressure of 755.2 millimeters of mercury over a specific time period. A total 1.02 liters of gas is collected. What mass of oxygen gas in grams is formed? So we are going to say by PV should be equal to nRT. We are going to have our pressure which is equal to a certain value. What we are looking for, the number of grams. So according to the subject of the formula, let's make mass the subject of the formula. So we have PV, number of moles, is equal to mass over the molar mass, then times my RT. So I'm going to make my mass the subject of the formula. So we are going to have PV times the molar mass, then we divide by RT. We have already done something similar to this, should be equal to our mass. So we are going to substitute. Now we are going to ask ourselves, what is the pressure? The pressure is given in millimeters of mercury. So we are going to say 755.2 millimeters of Hg. Converting it to ATM, we are going to divide by 760 millimeters of Hg times 1 atmosphere times the molar mass. So which gas are we looking at? Since the gas that we are looking at is oxygen, the molar mass of oxygen, it's 16. Oxygen gas by 2, it will be 32 grams per mole. Then over this, we are going to have our R value, which is 0.08206. Then times our temperature, which is given as 293 kelvins. This should be equal to our mass. So when we do our calculation, we are going to end up with, on top, we are going to have a 31.7978. When we divide by 0.08206 times 293, we are going to end up with a 24.04. should be equal to our mass. So when we divide, we are going to end up with mass is equal to 31.7978 divided by 24 will give us 1.52. 1.52. Sorry for that. Not 1.52, but 1.323 grams. So this is how we can find the mass for that one. Question 13. A steel tank has a volume of 438 liters and is filled with 0.885 kg of oxygen. Calculate the pressure of oxygen at 21 degrees Celsius. So we are going to do our calculation. So we are going to say from the ideal gas law, pressure should be equal to nRT over our volume. So we are going to have our pressure should be equal to what is our N value. Our N value, which is the number of moles, is the same as the mass over the molar mass. Since we have the mass times RT, then we have over the volume. So we are going to say the pressure should be equal to what is our mass. Our mass is 0.885 kg. Now kg is the same as times 10 raised to the power. The kilo is 10 raised to the power 3. So we have the 10 raised to the power of 3 grams instead of saying kg, because for the more concepts we use the mass in grams over the molar mass of this substance, which we are provided that the volume of oxygen. So the oxygen has got the molar mass of 32 grams per mole. Then we are going to multiply by what is our RT. Our R value is equal to 0.08206. Then we have times what is our time. Our time is 21 degrees Celsius, then plus our 273.15. So over what is our volume. Our volume, according to the question, it's equal to 438 liters. So our pressure will be found to be equal to, let's multiply the top part. So we have on top, we have 21362.084. Then we divide by what is our 32 times 438. So when we multiply those, we are going to get a 14016. So when we divide these two, we have a 21,362.084 divided by 14016. This will give us a value of 1.52. The pressure has to be in atmospheres. So we have found our pressure in atmospheres. Let's look at question 14. So to apply a green chemistry approach, a chemical engineer uses waste carbon dioxide from manufacturing process instead of chlorofluorocarbon as a blowing agent in the production of polystyrene containers. Find the density in grams per liter of carbon dioxide and the number of molecules per liter at standard temperature and pressure 0 degrees and 1 atmosphere. So we want the density. So if you remember the formula that we derived for density, we found it to be density times R times T should be equal to the molar mass times the pressure. So to find the density, we are going to divide over RT. We are going to have our density. Density should be equal to the mass, the molar mass times the pressure over the RT. So now we are looking at carbon dioxide first. So carbon dioxide has got a molar mass of 44.01. So you'll find that oxygen is 16 times 2, then carbon is 12.01. When we add these, we are going to end up with 44.01. So the density will be equal to 44.01. Then times, what is our pressure? Our pressure is 1 atmosphere. According to this, the first condition, we have 1 atmosphere. So we can say 1 atmosphere, then over our R value is 0.08206, then times what's our temperature? It's 0 degrees Celsius plus 273, which is the same as just writing 273.15. So our density, when we do our calculation on top, it will be 44.01 over 0.0206 times 273 will give us a 22.417. So the density, when we divide these two values, we are going to find that it is equal to 1.934 grams per liter. So now how do you find the number of molecules? You use Avogadro's law. Knowing that in carbon dioxide in STP, it has got the molar mass of 44.001. So this is the same approach we are going to use. So we are going to say, as long as you have a mass of 44.01 grams per given liter, you are always going to have the Avogadro's constant 6.023 times 10 raised to the power 23 particles, or rather molecules. So as long as the mass is complete, that is Avogadro's law. So we have those number of molecules. So we are going now to say, how about if you have 1.934 grams per liter, or this one should be equal to, we don't know. So we are going to cross our multiplication. So we are going to have our x times 44. We are going to have 44.01 grams per liter times x should be equal to 1.934 grams per liter times 6.023 times 10 raised to the power of 23. The power of 23. So we divide by 44.01 grams per liter over 44.01 grams per liter. So when we divide this, we are going to end up with our x value to be equal to, this will be equal to 2.69 times 10 raised to the power 22 molecules per liter. Let's look at the other one. So for the other one, we are going to do the same. Let's find our density. So density, according to the subject of the formula that we have already made, is equal to molar mass times pressure. So we have the molar mass times pressure over, we have over RT. So we have the density. This time we are calculating the density of the same substance. Now the temperature is 20 degrees and 1 atmosphere, same. So we are going to say the molar mass 44.01 times the pressure is 1 atm, it hasn't changed, over the gas constant 0.08206 times what is the temperature. The temperature is equal to we have a 20 degrees Celsius plus 273.15. So when we multiply this, when we divide this, we are going to get, so we have 44.01 over 0.08206 times 20 plus 273.15. This will give us a value of 24.055. So when we divide this, we are going to get a 1.83 grams per liter. So if we have this amount, we are going to form another relationship. So as long as you have a complete molar mass, 0.01 grams per liter, so this is the same as density. So as long as you have this complete density, we are always going to have 6.023 times 10 raised to the power of 23. Then how about 1.83 grams per liter? This will give you don't know. So we are going to multiply. So we have a 44.01 grams per liter times x should be equal to 1.83 grams per liter times 6.023 times 10 raised to the power of 23. Then we divide by 44.01 grams per liter over the 44.01 grams per liter. So we are going to find that our x value will be found to be 2.5 times 10 raised to the power of 22. So question 15 says that a flammable gas made up of only carbon and hydrogen is found to effuse through a porous barrier in 3.5 minutes under the same conditions of pressure and temperature and pressure. It takes an equal volume of chlorine gas 7.34 minutes to effuse through the same barrier. Calculate the molar mass of the unknown gas and suggest what this gas might be. So now, from chemistry, we know that the rate of chemical reaction is equal to the amount of substance that is used up, but in this case, it's the amount of substance that effuses over the time taken. So from this, you may establish to say the rate will share an inverse relationship with the time. Now here, this question is asking us to apply the concept or the principle of Graham's law of effusion, which states that the rate is inversely proportional to the square root of the molar mass. So meaning to say the rate of any given gas is inversely proportional to that molar mass. Therefore, the equation connecting rate and the molar mass according to Graham's law is rate number 1 over the rate number 2 should be equal to the square root of the molar mass. Now rate 1 will correspond to the molar mass of 2, since these share an inverse relationship. So if we have rate 1 on top, we are going to have molar mass number 2 there, then down we are going to have the molar mass of 1. So this shows that we have an inverse relationship. Now, since the rate and time have got an inverse relationship, it means to say the time taken for a gas to effuse is a direct relationship to its molar mass. Meaning to say, if you have the mass of 20 comparing it with the mass of 50, this one will take more time. It will take, let's say, about 50 minutes for it to effuse. This one, let's say it will be something like 20. So the bigger the mass, the more time it will take. So that's the relationship between time and the molar mass. So that when we use time, we are going to say the molar mass number 1 over the molar mass number 2. So now, since we have this formula and we are provided with time, we are going to produce the relationship. From the question, we know that we have a 3.5. We have a 3.5 as our time taken for the unknown gas to effuse over the 7. We have 7.34. This is the time it takes for the gas of chlorine gas to effuse. Should be equal to the square root of what is our molar mass. So we have established that our molar mass for the unknown gas is unknown. So we are going to just put molar mass number 1 over the molar mass of chlorine. So remember, this is the mass of chlorine. It should correspond to the mass of chlorine if we are provided with time. If it's rate, we could have used an inverse relationship. So the molar mass of chlorine gas is diatomic. Therefore, it will look like this. So we have a 2 times 35.5, which will be 2 times 35.5 will give us a not 35.5 according to A levels. We are supposed to use 35.45. When we multiply these, we are going to get 70.9. So this 70.9 will be here, 70.9, which is our chlorine gas. Then we are going to, since this is the square root, we are going to square so that we remove the square root on both sides so that this and this goes. So we have 3.5 divided by 7.34. This one will give us a value of 0.477 inside the brackets. Squared should be equal to the molar mass 1 over the 70.9. So we are going to have a 0.477 squared, which will give us a 0.22744529 should be equal to the molar mass number 1 over 70.9. So we are going now to cross multiply. So when we cross multiply, we are going to have 0.2274529 times 70.9 should be equal to the molar mass number 1. So when we multiply these, we are going to find that our molar mass number 1 will be a 16.13 grams per mole. So now, which gas would correspond to this? This is only made of carbon and hydrogen. Now we know to say, since it's 16 and the mass of carbon is 12, if we cannot have 2 carbons, if we have 2 carbons, the mass will be somewhere 24.02, of which it means to say the carbon we should have 1. So if we have 12.01, we need an element which, how many? So we need about 4 hydrogens to reach 16. And hydrogen, the molar mass for hydrogen, it's 1.01. So we are just going to have 12 plus that. We are going to have find out that this will correspond to the unknown gas. So if we add a 12.01 plus 4 times 1.01, we are going to find that our answer will be, here it's giving us a 16.05, which is very close due to the fact that we are rounding off numbers. That's why it's so different. But in any case, if we are to round this to 1 decimal place, it will be 16.1. So the unknown gas is concluded to be methane. Looking at the next question, it says that calculate the pressure exerted by 0.5 moles of nitrogen in a 1 liter container at 25 degrees using the ideal gas law, using the Van der Waals equation, for which A is equal to 1.390 and B is equal to 0.0391. Then we are told to compare. So using the ideal gas law, which ignores, so the difference between the ideal gas law and the Van der Waals equation is that under the ideal gas law, we are going to assume that particles do not interact. the particles or the gases do not interact. Why don't they interact? This is simply because we assume that they are always moving at a very fast speed with no time to interact. But under the real gas behavior, sometimes gases might be moving at a slow rate. And if they are moving at a slow rate, we are going to find that at one point, since they are moving, they might repel or attract each other because they are moving at a slow rate. The other assumption about ideal gases is that ideal gases do not have volume, or in other words, the volume of ideal gases is negligible. Now, this is more like you have something like on Earth, we only have, let's say, one person. So you would think that the space or the volume occupied by that person is too small for it to be considered. Now, under real gas behavior, we are going to have different gases. When they compress together, or rather a lot of them, they can form some distinct volume because of them being close to each other or being a lot of them and confined in a space. So that's the difference. So now, due to this, there is a difference in the results that come out under ideal and the real gas behavior. The real gas behavior is slightly less than the ideal gas value, because under the ideal gas behavior, we are going to assume that there is some loss of volume of the container. Like, for example, under the real gas behavior, we are just going to assume to say the volume of the container is the whole thing. Now, under the ideal gas, in order for us to calculate more like the volume of the container, we have to subtract the volume more like the particles that are interacting occupy. So due to that difference, there is even the difference in the value produced. So the first part, the ideal gas way, we are going to say, we know that ideal gas equation is PV should be equal to nRT. So our our pressure will be equal to nRT over the volume. So the number of moles, according to what we have been provided with, it's 0.5 moles. We have the R, which is our 0.08206 times the temperature, which is our 25 degrees Celsius plus 273 degrees to convert it to the kelvins. So we have 273.15 degrees over our volume. Our volume of the container, we have been provided that it is equal to 1 liter. So we are going to find that when we multiply 0.5 times 0.08206 times 25 plus 273, our outcome will be a 12.233 atmospheres. Because even if we divide the 1 liter, 1 doesn't change anything, and the units for pressure, when we use this value, if also the volume is in liters, it will be in atmospheres. Let's look at our B. Under the real gas equation, the ideal gas formula is P plus A open brackets N over V squared. We close, then we have our V minus NB should be equal to nRT. So we are going to make pressure the subject of the formula. So the pressure will be, so we have pressure plus A N over V, we square this, then we have should be equal to nRT. If we divide V minus NB, we divide V minus NB, we are going to have V minus NB. So we have this. Then finally, we have P plus A N over V squared should be equal to nRT over the V minus NB. So we are going to get this component and move it to the other side. So we are going to have pressure should be equal to nRT over the V minus NB. Then we have minus A N over V squared. So this is the equation for pressure under the real gas equations. So our P should be equal to our n value is 0.5 times 0.08206. Then we have times the temperature, 25 degrees Celsius plus 273.15. Then we have minus, what's our F value? Our F value, according to the constants that they have given us, A is equal to 1.390. Then we have our number of moles is 0.5 over the volume is 1 liter. Then we square this. Then here we are going to divide 1 liter minus number of moles is 0.5 times the B constant. B constant was given as 0.03191, like that. Now if you look at what is on top, this is not different from what we multiplied at first, and the answer we got was a 12. If we multiply, we have this one, 12.233, then over, we are going to have 1 liter minus this value. So we have 1 liter minus, so 0.5 by 0.0391, we are going to have 0.01955. So then we have minus, when we divide 0.5 squared, so we have 1.390. 0.5 squared, we are going to have a 0.25. So when we divide, we have pressure should be equal to 12.233 over, we have our 1 minus 0.01955. This will give us a value of 0.98045. Then we have minus, when we subtract 1.390 times 0.25, the value when we multiply those, we are going to get 0.3475. Dividing these two, we are going to get, so 12.233 divided by 0.98045. This will give us a value of 12.477. Then we have minus 0.3475. When we subtract these two, our pressure will be amounting to, so 12.477 minus 0.3475. This will give us a 12.13. So now, atmospheres. So now, if we are to compare the difference, we are going to find that the ideal gave us a value of 12.233. The real gas, the actual volume or the actual pressure is 12.13 atmospheres. So what happens to the other pressure? The difference of 12.233 minus 12.13. So these are in atmospheres. So when we subtract these, we are going to find that we are going to get a difference of 0.1. So this pressure might have been lost from the way the gases are interacting. Remember, pressure is the force per unit area. Now, if those two gases begin to interact, they will not be producing pressure against the container. So that is what could happen to this other pressure. Thank you very much for watching the video. Hope you would like, subscribe, and share for more. See you in the next tutorial.